Hello everyone, welcome to Reactify Labs. In this video, we will talk about database selection. Means we will see what are the different types of databases, what are the use cases for which each of these databases are suitable, and what are the systems which use what kind of databases. Okay. So this video is more about talking about different databases on a high level and what kind of use cases suit each kind of database. Okay, so let's start with the structure that we are going to follow today. First we will start with the introduction, like why do we need to talk about database selection. Okay, next we will see what are the common types of databases. Okay, next we will see what are the factors which influence database selection. Factors influencing database selection. Next, we will see what is the internal implementation of databases. Next, use cases and database selection. Next, we will see the real world examples. And then we will see what challenges do we face while doing database selection. Challenges in database selection. Okay. In the interviews, we very easily say, okay, we will use SQL database here, or we will use NoSQL database here, or we will use time series database here. But is it this easy? Is it this easy to just say this kind of database we are going to use? No. Now today we will see what are the considerations that we need to take care of and why it's not easy. Okay, even for experienced engineers it's not easy. We need to weigh a lot of things. We need to do trade-offs on something or the other, and that's how we choose our database. Okay, now let's start. First, introduction. Choosing the right database is more than a technological choice. It's a critical decision that deeply influences the success of applications, impacting their efficiency, scalability, and overall performance. Okay, efficiency, scalability, and thus overall performance. So that's why choosing the right database is essential. The internal architecture of a chosen database has a substantial impact on day-to-day operations. So that's why I said we will talk about the internal implementation of the DBs, because we should know how databases are implemented internally. Only then we will be able to know, okay, this internal implementation is going to help in fast writing or fast reading or something else, right? So from data retrieval to system maintenance, the efficiency and ease of these operations are intricately tied to the internal workings of the selected databases. Okay, now let's see what are some of the common types of databases. Common types of databases. First is relational database. We all know about it. We even study it in our undergrad in the database management systems topic. It's ideal for structured data which has predefined schemas. I'm not going to talk in detail about these because I have made a separate video. I think it's titled as SQL versus NoSQL. In that I have covered all these databases in detail. Please go and watch it if you haven't watched it already. Next is NoSQL databases. So NoSQL databases, these are suitable for unstructured or semi-structured data, providing flexibility. Next, we have in-memory databases. In-memory databases. They are designed to store and retrieve data from the system's main memory for faster access. Next, we have time series databases. So they are specialized for handling data points indexed by time. And next, graph databases. So they are optimized for storing and querying interconnected data. Okay. Now let's see what are the factors which influence our selection of database. Let's see factors influencing database selection. Factors influencing database selection. Okay. First is data model. So the chosen data model, be it relational, document oriented or graph, directly influences how data is structured and queried, making it a very important factor in determining a database's suitability for specific tasks. Next is scalability. The internal scaling mechanisms, whether horizontal or vertical scaling, significantly impacts a database's capacity to handle growing datasets and increased workloads. Next is consistency model. The decision between ACID and base model depends on the application's requirements for data consistency. If you don't know what acid and base is, it's not the acid and base from chemistry, it's the acid and base from databases. Please go and watch that video as well. I have a video on acid and base. Okay. I think it's either a separate video or it's in the same video as SQL and NoSQL, somewhere there. Okay. Or I think there is another video on consistency models. I'm not sure. Please go and check that. Okay. And next is workload type. Whether the system is read heavy or write heavy influences the database selection. Some databases are optimized for efficient reads, while others excel in write intensive scenarios. Okay. Now let's see the internal implementations of the database and how it affects the performance. Internal implementations and performance. So first is storage engine. So here the examples are, first is LSM trees. So LSM trees is called log structured merge trees. They are used in write heavy systems to optimize write operations, reducing disk IO. And second is B trees. So B trees are efficient for read heavy workloads, providing quick access to specific data points. So we need to see if for our database the internal implementation is LSM tree or B trees. If our database needs to be write heavy and less read, then we need some database actually if our application is something which is write heavy, then we need a database for which the internal implementation is LSM tree. Okay. Similarly, if our database is read heavy and it has less writes, then in that case we need to have a database which has B tree as its internal implementation. Okay. Next, indexing strategies. Indexing strategies. So here the examples are B tree indexing. It is suitable for read heavy workloads, allowing efficient range queries and point lookups. And there is another called bitmap indexing. It is effective for read heavy scenarios, especially when dealing with low cardinality data. Okay. Now let's talk about the use cases and database selection associated with them. Use cases and database selection. First one is transaction intensity. Applications with high transaction intensity involving complex and interconnected data manipulations may find relational databases more suitable. Relational databases offer strong asset guarantees, ensuring the consistency and reliability of transactions. For example, MySQL, Postgres, Oracle. Okay, I'll write MySQL, Postgres, Oracle. These. Next is read heavy workloads. For workloads where the majority of operations involve reading data, databases with efficient caching mechanisms or those optimized for in-memory storage becomes more appropriate. In-memory databases, for example, excel in scenarios where rapid data retrieval is very important, making them well suited for read-heavy applications like Redis, Memcached, okay, MongoDB, okay. Next, write-heavy workloads. So, in contrast to read-heavy workloads, applications with a significant focus on write operations such as logging systems or real-time analytics capturing continuous streams of data may benefit from databases optimized for high write throughput. NoSQL databases, especially those employing LSM trees or LSM storage engines, are designed to efficiently handle write-heavy workloads. Examples include Cassandra, okay, DynamoDB, etc. So you might be wondering what is this LSM tree that I am talking about. I'll talk about it in later section of this video. Okay. Next is complex queries and analysis. If we have this kind of requirement, complex queries and analysis. So for applications that involve complex queries, data analysis and aggregations, databases supporting advanced query languages and analytical functions are preferable. This is often seen in scenarios like business intelligence applications or systems requiring extensive data analytics. For example, Google's BigQuery, Amazon's Redshift, Snowflake. These are good. Okay. Next, time series data. So time series databases are well suited for applications dealing with data points indexed by time, commonly found in IoT, monitoring, and financial systems. They efficiently handle time-based queries, aggregations, and analytics, making them a natural choice for time-dependent datasets. Examples include OpenTSDB. I think there is one called Timescale DB also. Prometheus. There is one Influx DB also, if I'm not wrong. Okay. Now let's talk about LSM trees. Okay. So what are LSM trees? So LSM trees. What are LSM trees? So LSM trees, also called log structured merge tree. Log structured merge trees. So LSM trees stand out as a data structure tailored for write intensive workloads, particularly in databases dealing with frequent write operations, as I told before. Okay. It has different components. So what are the components? So first one is memtable. An in-memory structure acting as a staging area for incoming write operations. It provides rapid write access. Next is SS tables. So SS means sorted string. Okay, SS tables is sorted string tables. This is immutable on-disk storage that contains sorted key value pairs. SS tables ensure durability and are organized for efficient range queries. And next is compaction. So the process of merging SS tables to enhance read efficiency and maintain optimal performance. Compaction helps manage disk space usage. So basically what happens is any write happens to the mem table, okay? The write goes to the mem table, and periodically this mem table writes to SS tables. And why SS tables? Because to persist, okay? SS table is basically in the disk, and when you write to the SS tables, it persists there, okay? And later you can read from there. So what happens here is, if you have to just write to the mem table, what it does is it just adds, LSM tree is basically a tree, okay? So if you write something, let's say here it creates a new node and writes to it. So it's easy to write, right? So it will just find where to add a new node and it will just write it. So that's why write is very fast here. But read is slow. Why? Because you have to read it from the SS tables, and SS tables is in the disk. And if you have to read from the disk, it's a costly operation. Okay. So that's why I said before also, LSM trees are the internal implementation of databases. If LSM trees are the internal implementation, it means those databases are good for write heavy operations. Okay. Let's see the use cases and characteristics. Use cases and characteristics. So write intensive workloads. LSM trees excel in scenarios with high volumes of write operations due to the efficient write amplification achieved through the mem table and SS table design. Okay. Next is distributed storage system. Widely adopted in distributed storage systems where handling numerous write operations concurrently is crucial for performance. Next, compaction for read efficiency. Compaction is a key feature that ensures LSM trees maintain efficient read access over time by minimizing fragmentation, right? Yes, compaction makes the read faster, but faster than what it would be without compaction, okay? Still, it's slow compared to other databases which are specifically designed for read heavy operations, which use B trees. I'll talk about it in some time, okay? So it was 3. And next is durability and reliability. So the immutable nature of SS tables, this SS table is immutable, okay? The immutable nature enhances data durability, making LSM trees suitable for applications that prioritizes data reliability, okay? Now let's talk a little about SS table. SS tables. So SS table is basically a file format often used in LSM trees. It provides an immutable and sorted storage structure. So what are the characteristics of this SS table? Okay, the characteristics are sorted order. The key value pairs within SS tables are sorted, enabling efficient range queries. However, the benefit of sorting for reads comes with a trade-off of additional complexity and time during write operations. Next is, it's immutable. SS tables are designed to be immutable, meaning once written, they are not modified. While immutability simplifies certain aspects like crash recovery and compaction, it may introduce overhead for certain read patterns, thus making read operations slow. And compaction. Periodic compaction processes are required to merge and organize SS tables, which can impact read performance during these operations. Now let's talk about B trees. So I am pretty sure most of you have studied B trees in your data structures subject, but still let's talk about it. So B trees are self-balancing tree structures designed for efficient searching, insertion and deletion operations. Okay, so the characteristics of B trees are balanced structure, node structure, ordered keys and self-balancing. Okay, so B trees maintains a balance between depth and number of keys in each node, ensuring consistent performance for search operations. Each node in a B tree has a variable number of keys and child pointers, allowing for flexible adjustments to maintain balance. Keys within each node are ordered, facilitating binary search for efficient retrieval. And B trees automatically adjust their structure during insertions and deletions to maintain balance, ensuring logarithmic time complexity for operations. So if you remember from your lectures about the B tree, class lectures, not my lectures, I have not made any video on B tree yet. So it is B tree. B does not means binary here. Okay, so let's say this is a root which has one node, then its children, let's say this child has 3 nodes, this child has 2 nodes, this child has 3 nodes, then each child has some nodes, right? So it happens like this. So let's say if this one has, okay, this cannot have, this can be 10. Okay, so left of 10, so yeah, it has to be only 2. So left of 10 can be, let's say 2, 5 and 8. Okay, so any child, okay, anything which will be a child of this, okay, this 2 should be less than 2. Anything which is a child of, let's say this is this 5, should be between 2 and 5. Okay, here again anything it should be between 5 and 8, and anything here should be more than 8. Okay, so it means it follows what that we use in BST, right? In that it only has 2 nodes, I know, in BST, but it's the similar thing. Anything which comes from here has to have the numbers between this node and this node. Anything which comes here has to have the numbers between this node and this node, means greater than this and less than this. Anything to the right of something should have greater than that value. Okay, so the same thing is followed in B trees, and due to that, let's say the tree grows very big, and B tree has specific a peculiar nature that it balances itself. Let's say if there are too many nodes here, so it will break it into two. It will send some node to the top and like try to maintain a balance. Okay, and due to that, what happens is it's always height balanced. Okay, it's height balanced, and everything, since it's in order, as I have written here, it's ordered keys, we can do a binary search. Okay, so no matter where the node is, it can be done in log n time. Okay, so that's why it's good for read heavy operations. If the internal implementation is B tree based implementation for the database, it means it will be a read heavy database. Okay, why? Because of the height balanced nature, self balancing nature, node structure and ordered keys, due to which binary search is possible, and binary search is something which makes this a read heavy system. And why not write heavy? Because if you have to write something, let's say you write something here, then what happens is it needs to check a lot of things. Does it follow the convention, right? Like if it goes between these two, let's say here it's 5 and 8, if you need to add 7 here, then what happens is it needs to first create a new node, create a new space between them, and then needs to fill it. And then what if there are too many nodes at this level, then it may need to break this and break this into 2 parts and then send this to the root node, or come when you send it to the root node. And then if root node again is a lot, then again it needs to break the root node and send it to the top, creating a new root. A lot of things happen in B trees. That's why this is not good for write operation. Okay, and that's why it's good for read heavy systems and not write heavy systems, because write is slow. It's not that write is not possible, it's slower. That's why if you have less writes, and more reads, then you can prefer this kind of database. Because if we have less writes, we can deprioritize writing operation. We can say that, okay, if you write now, maybe your write will be visible after 5-10 seconds, but the reads, we will provide this data within milliseconds. Okay, so this was all about B trees. Now let's talk about hash index. Hash index. So hash index is a data structure utilizing a hash function to map keys directly to storage locations, ensuring constant time complexity for access operations. So the characteristics is direct access. As you know, as we do in hashing, hash map or indexing in the databases. So everywhere hash index is used. Okay, not not exactly actually. Sorry. When I say hash map, what hash map does is, if I have to talk about it, let's say you have a hash map. So and if you add, let's say for key 2, the value is, let's say, ABC. Okay, so what it does is it basically takes 2, hashes it with whatever algorithm it has, and maps it to a memory location. Okay, memory location. And next time when you just query like what is the value of hash map 2, it just again does the hash, go to that memory location, direct access, and gets that. Okay, so that's what hash index also does. It gets direct access, enables direct access to data by applying a hash function to the key, providing a constant time complexity for both read and write operations. Next, collisions, because anywhere there is hashing, there will be collisions. It's unavoidable. Collisions occur when multiple keys hash to the same location. Effective collision resolution mechanisms like chaining or open addressing are crucial for maintaining data integrity. And next is memory efficiency. Memory efficiency. Hash indexes are memory efficient, requiring less storage compared to structures like B trees. Okay, and limited to equality queries. Yes, this is a very important point. Limited to equality queries. Most effective for scenarios where equality queries are prevalent, but less suitable for range queries due to the scattered distribution of hashed values. Okay, why? Because when we hash something, let's say we have different data, 2, 3, 4, 5, 6, 7. These are the keys which we need to hash. 2 maps to a memory location here, 3 maps to a memory location here, 4 maps to a memory location here, 5 here, 7 here, and 6, let's say, here. Okay, now what happens is, if you just want to see what is the value of the key 5, then what you will get is, yes, it will be hashed and the particular memory location's value will be given to you, right? Whatever the value in that particular memory location which is given by the hash. But if you want to know what all are the values which are smaller than the value in the 5, okay, so in that case the 5 has a different location, 4 has a different location, 3 has different location. So it means it needs to go through the entire hash keys to find out the like less than or greater than or something, anything which is not an equality comparison. Okay, so that's why it's limited to equality queries. So in databases, it's a common thing. We say that if you have to perform something like, if you have to query something like less than this or greater than this, then it's better not to index that, because indexing only makes that operation complex. Okay, if there are a lot of equality comparisons, then indexing is a good choice there. Okay, let's talk about the use cases of hash indexes. First is high speed retrieval. It's ideal for scenarios demanding fast and direct access to specific records. Okay, next is unique key lookups. Unique key lookups. It is efficient for unique key lookups where each key maps to a distinct hash value and in-memory database. Commonly used in in-memory databases due to their swift access times. Let's talk about some of the real-world examples and what kind of databases they use. real world examples. First is LinkedIn. So LinkedIn utilizes relational databases for structured data like user profiles, because user profiles are constant, right? Like you will have a name, you will have a company where you work, you may have like email ID, password. It's common for everyone. So that's why structured data is good here. But it leverages NoSQL database for unstructured data such as activity feeds and recommendations. Similarly, Facebook. It uses MySQL for structured data storage, again, like your profile, but unstructured data for again activity feeds and recommendations. And also, it has to take care of geographical distributed data management. So, it needs to distribute data across different nodes. So, it uses some databases like NoSQL databases, which are good for horizontal scaling, right? Next, Netflix. It relies on Cassandra for high write throughput and manages user preferences, streaming history, and recommendations with different types of databases for each of these. Okay. Now let's end it with talking about what are the challenges that come with selecting a database. Challenges. First is diverse application needs. Navigating complex data requirements which arise from diverse applications is a problem, because it's possible that your system may have different types of data. Again, structured data, unstructured data. You may need to read, you may need to write as well. So sometimes it's possible that your task cannot be achieved by one kind of database alone. You might need to use SQL for something, NoSQL for something else. And even in NoSQL, let's say you have to use one kind of database for read heavy operations, one kind of database for write heavy operations, different kinds of things you need to take into consideration. Okay. Changing workloads. Adapting to dynamic workloads with varying read and write operations is also something to consider. Skill requirements, definitely. So meeting skill requirements for adopting databases with specific internal implementations is essential. It means you should choose those databases which like in which your team is proficient, your team knows, or they are good, the learning curve is not very steep, at least somebody knows how to use, or somebody has experience in using those databases. You would prefer those, right? Next is scalability planning. Addressing challenges in predicting accurate scalability requirements, like what kind of scalability your system is going to handle. Because let's say if you have only 1,000 users, you are not going to use NoSQL databases and geographical distribution of databases, right? You are not going to worry about sharding, right? So you have to consider these things as well. And integration challenges. Integration challenges. So overcoming issues related to integrating databases into existing systems during transitions is also important. Okay. So yeah, this video now concludes, and I have covered almost everything about everything to keep in mind while selecting the database. So yeah, this became a very long video, but it contains everything. So now when you talk about like the kind of database you are going to use in your system design interview, you can now justify them with these reasoning, like yes, my system is going to be a read heavy system, so I'll use some kind of database which has this LSM tree based implementation. And similarly for write heavy, you will use B tree based implementation, and these are the databases which are implemented using LSM tree, and these are the ones which are implemented using B tree, different kinds of things, right? So yeah, that's all there was in this video. I hope you liked it. So yeah, that's it. Thank you for watching. Please remember to like, share, and subscribe. I will see you in the next one.